title is Electrochemical Surface Science and Energy Conversion. And I'm going to introduce him briefly. And he got his Bachelor of Engineering from Applied Chemistry from Osaka University. Then master's degree from
교수님이랑 못 먹을 걸요.
the same university and PhD from Flinders University of South Australia. Then after his PhD,
Actually, before.
Even after his master's degree, he was a research chemist. I see. I'm sorry. After his master's degree, he joined Mitsubishi Petrochemical Company for 7 years, and at the same time, he's got his PhD. Then he went to Oxford University in organic chemistry laboratory in 1978 to 1980. Then he took a professorship at Hokkaido University, Sapporo, Japan, and then he stayed until 2020, I think. And during that time, he was a director of the Catalysis Research Center. Then from 2010, he moved to the National Institute of Material Science as a principal investigator. Then he became a fellow of NIMS in 2013. And during that time, he's also served as a director of Global Research Center for Energy and Environment based on nanomaterial science, then Center for Green Research on Energy and Environmental Materials. And since 2016, he was an executive advisor to the president of NIMS. And he's also currently a program officer, specially promoted research for innovative next generation battery, advanced low carbon technology R&D program of Japan Society of Technology Agency. And he received numerous awards, starting from Scientific Achievement Award of ECS Japan. Then 2010, he received a Chemical Society of Japan Award. And 2014, a Society Award, the Surface Science Society of Japan. And in 2015, he got an honorary doctor's degree of Flinders University, Australia. And 2016, and he was very honorably published a Kohei Osaki postscript in Journal of Physical Chemistry C of American Chemical Society. And he currently is a fellow of IUPAC, RSC, ISE, ECS, CSJ, published about 540 papers and 50 book chapters. And his research interest varies from catalysis, lithium battery, fuel cell, oxygen reduction reaction, and interface structure. So please welcome Professor Osaki for his presentation. It's yours, Kohei.
Okay. Can you see?
Yes.
Okay, so let me start my seminar. So it is my great honor and pleasure to present this lecture. And I'm very thankful to Professor Hassa Kim for this arrangement. So as he mentioned, I started my career in academic life by doing the PhD in Flinders University of South Australia almost 50 years ago. So the title was for the electrochemical production of hydrogen. So this subject is still very popular among many researchers. At that time, of course, this Professor Bokris is very famous even at that time. And within this photo, the Dr. Levy, he's also very famous in the corrosion science. And the another friend is now later, he became a space astronaut, first space astronaut in Japan. So this photo was quite nice for me. But the thing I wanted to show here is this list. This is the introduction of my thesis, list of semiconductor investigated photoelectrochemically before my work. Actually, I want to mention this paper. This is by Professor Kim. So photo effect at polycrystalline tin oxide electrodes. This was affiliation with the University of Illinois at Urbana-Champaign. So it means this is a work of his PhD, right? So I must say I knew his name even from this time. And then we started a joint seminar between the Korean and Japanese electrochemists. So this is a photo of the second meeting held in the Iwanuma, which is close to Sendai, Japan, in 1995. I think even this is 27 years ago, you can guess where the Professor Kim is, where is me. So this is Professor Kim, 27 years ago. And this is me. And also you can find several Korean professors in these photos. Although the photo is not good, but the second one is better. So this is 13 years after the first photo. And this is the Seoul National University, Hokkaido University Joint Symposium held in SNU 2008. So 13 years ago and 13 years after. So this is a kind of photo in between now and the top figures, top photos. So actually, Professor Kim didn't change much, I guess. Little white hair, and I'm here to here. So anyway, so we are very long friends. So now I must start the scientific introduction. So nowadays, many people, of course, realize the importance of the energy flow from renewable energy to the daily life. And of course, the solar energy, solar cell or the windmill would generate electricity, then that electricity should go to the grid or but maybe stored in battery. But for the long-term storage, we need electrolysis to make hydrogen, and hydrogen can be converted back to electricity by fuel cell or used as a fuel cell car, etc. So this is a very modern or the future society structure, but I must mention my boss, Professor Bokris, wrote a book in 1975, Energy Solar Hydrogen Alternative. So he was very much looking forward the future even at that time. So I was very much influenced by him. So since then, I was also interested in energy related research. So as already mentioned by Professor Kim, that I was the director of Global Research Center for Energy and Environment and Energy based on nanomaterial science. We call it GREEN, which was supported by MEXT, Ministry of Education, Science and Technology, Japan, generally $2 to $3 million annually for 10 years. So in that, we studied the fundamentals of these devices. So now hydrogen and battery energy storage, and the battery electrolysis, fuel cell are all electrochemical energy conversion devices. So electrochemical energy conversion is very important. But before going to discuss the electrochemical energy conversion, I want to just say several words about the forms of energy. As you know, the energy can be converted each other. So the electric energy, mechanical energy, thermal energy, chemical energy, nuclear energy, magnetic or hot energy. So as far as electric energy or electricity is concerned, the electricity can be generated mechanical by converting mechanical energy to electric energy by hydro power generation or wind power generation. Thermal power generation, most used power generation is the chemical energy to thermal energy to mechanical energy to electric energy. Of course, chemical energy includes natural gas, petroleum, and coal. Then nuclear energy is, of course, mass change, but that's, again, it is converted to heat, then to mechanical energy to electric energy. So in both cases, actually, that the thermal to mechanical conversion is included. So it has a Carnot type of thermodynamic efficiency limitations. So now, the chemical energy can be directly converted to electric energy by using the battery or fuel cells. And vice versa, the electric energy can be converted to chemical energy by battery in charge mode or electrolysis water. So the battery or electrochemical energy conversion is the direct conversion of chemical energy to electric energy or vice versa. Of course, solar energy is converted to electric energy by solar cells. Now, this is the, of course, important equation for the electrochemical energy conversion. The electromotive force is determined by the free energy of the given reaction. So thermodynamics determine the this voltage generation. Because this is a direct energy conversion without thermal to mechanical conversions, the theoretical efficiency is relatively high. For example, hydrogen water fuel cell or electrolysis, which is the reverse reaction of fuel cell. This is actually the formation or decomposition of water from hydrogen to oxygen. So you can calculate the free energy of formation, and then theoretical electromotive force is 1.23 volt. So in this equation, there's no electromaterials involved, so this electromotive force is independent of electromaterials. However, if you look at the real situation, this is the hydrogen evolution in acidic solution at platinum, silver, and mercury. So in the case of platinum, actually, the hydrogen evolution started at theoretical potential, but silver required more potential to apply, and mercury requires more than 1 volt than platinum to be applied. So also in the case of battery, this is a lithium-ion battery which we are studying now. So in this case, from the free energy of formation lithium power side, we can calculate the potential or voltage is 2.96 volt. And even we can calculate the energy density from this free energy converted, because free energy is the kilojoule per mole, you can convert it to the watt-hour per kilogram. So this 3,450 watt-hour per kilogram is really high. So thermodynamics tell you what we can do by this battery systems, but again, in the case of battery or fuel cell, we need not only voltage, but power. Power means voltage multiplied by current. So electromotive force can be determined by reaction, but current is not. So this is, in this situation, this square gives you the power on this case, but in other cases, power is, maximum power is like this. In the other cases, this is very bad situation. Then when we run the current, potential drop very quickly. Those depend on the current, which is the current is the electron flux, which means reaction rate. So the higher the reaction rate, the better the performance. So the potential is thermodynamic, but current is not thermodynamic, reaction dynamics. For example, also, this is a fuel cell. This is the Toyota's Mirai car. So it's commercialized, but still the problem. So hydrogen, oxygen are converted to water in this case, and the potential is 1.23 volt. However, this is a theoretical lines, but once you start driving a car to take the current, potential drops. So this is due to the energy loss to flow current. So to improve these lines, we need catalyst. Catalyst is required to accelerate the rate and reduce the overpotential of electroreaction. So how to develop or how to design catalyst? To do that, actually, we need mechanistic study. So the electrochemical surface science was developed. So generally in chemistry, we learn that synthesis properties and structure relations are very important. So in these electrochemical reactions, of course, surface is involved. So the preparation of surface and surface reactivities and also structure include geometric, electronic, and molecular structures. Particularly in the case of electrochemical surface, the presence of solvent makes the situation worse or more difficult. So it is very difficult to prepare and maintain the clean substrate surface in solution. And also, of course, to measure the property or reactivity in situ in real time, and also the structure determination is difficult within solution. But it's already 40 years ago, but our generation really enjoyed this development. In 1980, Professor Courabille developed new technique to prepare single crystal ball. So before single crystal was very expensive and you need to use vacuum system, but he developed a technique to make relatively small, but still single crystal. So this is the single crystal ball, something like 5 to 6 millimeter or something like that. So these are the 111 phase. So you can use very nice clean surface, and by using the water drop, you can protect it by flame melt method. So, but for the measurement, also there are a lot of development. So for the surface observation, you need the photon or electron or ion or scanning probe as a probe. So in the case of nano structure or the solution case, you cannot use electron or ion probe because they interact so strongly with matter. So the X-ray is one of the very important techniques. And of course, scanning probe microscope. They are developed very nicely in the last decades, several decades. So these are the techniques applicable to the solid liquid interfaces. So these four are for determining the geometric structure, scanning tunneling microscope, atomic force microscope, and the X-ray techniques, surface X-ray scattering, and X-ray absorption fine structure. The electronic structure is more difficult to determine. The exhaust can be used, and second harmonic generation spectroscopy can be used, but both are relatively difficult, not straightforward. And the XPS is, of course, vacuum technique, but recent development allowed to use XPS by using the window separating vacuum and electrolyte rooms. The molecular structure can be determined by vibration techniques such as IRAS, SAS, and some frequency generation. In addition, sometimes you need the information of the surface film thickness or the surface weight changes. So these are the techniques we also contributed much to develop this technique, and also we access to the radiation sources. So thanks to the this technique development, we can now approach the electrochemical surface relatively easily and precisely. So we can say now electrochemical surface science is developed quite nicely. So this is the Web of Science showing that I searched for the electrochemicals for electrochemistry and surface science. The first peak is around 1990, 80s. Then the second peak comes in 1990. Of course, it's also developing recently. But in Japan, we have developed, contributed much by organizing the priority research on electrochemistry of ordered interfaces. It's already also about 25 years ago. But so is Professor Hashimoto, and so the various important people here. Actually, this is the Professor Wang in China. He is the now senior editor of JAX, and also the very famous professor in China. At that time, he was a postdoc just carrying this banner. But anyway, so we published and contributed. So this is the slide I always showed when I was a professor in Hokkaido University. So I was in our group, we always said that we want to design, construct, and observe the surface material phases in atomic molecular resolution, and then understand the electron transfer. And then that will be applied to this part. So first, I just show this one example for the how useful surface technique or surface electrochemistry to understand the phenomena at the electrode-electrolyte interface. So this is relatively old, but still, I think, very important results. So this is the palladium deposition on gold 111 single crystal. So this is the STM scanning tunneling microscope image in solution. The left-hand figure shows the without palladium tetrachloroparadate in solution. So the individual gold atom can be seen. Then by adding this solution, the surface image changes drastically, and it agreed with this structure corresponding to the adsorption of the tetrachloroparadate. Of course, this doesn't mean, or it means the tetrachloroparadate adsorbed in this way, but it doesn't mean it adsorbed monolayer. So we used electrochemical crystal microbalance to study the weight change. So by adding in this configuration, the electrode is the coat covered with gold, so that the tetrachloroparadate adsorbed on the surface, the resonance frequency goes down, so you can convert it to the weight change, which is 87 nanogram per square centimeter, which corresponds to the monolayer of this structure. So it is confirmed that the monolayer of the this molecule adsorbed on the surface. Then we scan the potential negatively so that the palladium atom adsorbed on the surface. This is the cyclic voltammogram, and this is the weight change calculated from frequency change. And then by integrating the charge and then plotted against weight change, it is linear. This is the Faraday law. The slope shows that this is 53.2 gram per Faraday, which means 2 electron deposition palladium on the surface. So by doing this, you know the metal is deposited. Then we also carried out electrochemical scanning tunneling microscope to see how it deposits. You can see here the as soon as potential pulse from here to here, immediately the single layer or monolayer of palladium is deposited, and the second layer starts to deposit, and so on and so forth. So we can follow also the metal deposition in solution in real time. The X-ray diffraction after the 7 layers of a palladium deposit shows that we have a palladium 111 peak only. So it means the palladium deposited epitaxially on top of gold 111 surface. But then the question is, the size of gold and the size of palladium different. Palladium is 4% smaller than gold. So this shows, of course, the diffraction peak corresponding to the palladium 111 peak means that the 70 layers of palladium deposited epitaxially, but with the palladium distance. But what happens for the first layer? The first layer is the palladium mass deposit on top of gold 111. Even from the first layer, palladium deposit with the distance between the palladium or the distance corresponding to the gold. So we carried out surface X-ray scattering using the synchrotron radiation. Surface X-ray scattering can be divided into two. One is surface X-ray diffraction. So the X-ray is coming in and diffracted with the surface structure, and the other is crystal truncation rods like this, so that we can get 3D information. In the bulk X-ray diffraction, we see only this black peak, but in the case of surface X-ray scattering, the information of surface can be obtained from these regions. So we did a lot, but make the story short, actually we found that the first palladium deposit on the FCC side of gold, which means palladium distance is of gold distance, not palladium distance. But by depositing the 5 layer, it already starts the palladium diffraction peak. When it is only 2 layers, 2-3 layers, when it is 3 layers, we don't see the palladium peak. So the first few layers, the palladium deposit on top of the gold, but then converted to palladium layer. But this first few layers have very unique catalytic activities because of the different geometric and electronic structure. This is the electrocatalytic activity for homoaldehyde oxidation for the 8 monolayers and 0.1 layer. And this is called bare gold surface. Of course, bare gold surface is not active for homoaldehyde oxidation. And 8-7 monolayer behavior is very similar to the palladium bulk 100. However, in the case of 0.5 monolayer, actually the activity is higher and much higher peak was obtained. So the first layer is quite different from the bulk palladium. Thus, we use also the other spectroscopic technique to show that this is due to the more electronic effect. Anyway, so I don't go to this detail. You can also see these by, I think you record and you see this my slide. You can take this information from this. And also we carried out the monolayer or molecular structure change in scanning microscope, surface X-ray, and so on. So we see the thiol monolayer formation on top of gold 111, how the atomically it's shifted, and the structure is different with the substrate is 111 or 100, and even also we can see the individual molecules in the case of alkane, and also how the when the thiol molecule absorbed on the surface, gold 111, the first layer structure changed from the root 3 by 23 reconstructed structure to 1 by 1 by surface X-ray diffraction. So, but now I'm more important part of my talk, which is the electrochemical energy conversion. So the electrochemical surface science is for the they are to bridge the ideal surface to bridge to the real world. Again, this is the one I showed. So these are the electrochemical energy conversion devices. So first, I would like to talk on the electrocatalyst related to the fuel cell and maybe on electrolysis. Of course, in Korea, the government is very much putting effort on hydrogen. I know that. And these are the fuel cell for the stationary fuel cell in the 2007 to 2018 globally. It's including a lot. And also this is the fuel cell car, the real number and prediction. Both are increasing, expected to be increased. But of course, the question is where the hydrogen should come from. So currently hydrogen is coming from the fossil fuel, which means it is not green hydrogen. So the water electrolysis, again, the electrochemical devices expected to play important roles. So it's expected to increase quite a lot. So now, as I mentioned, the theoretical potential goes down as far as you flow the current, which means you run the car. So particularly the loss is due to the cathode. Cathode means oxygen reduction. You can see from here, this is the model of the PEM fuel cell. So this is the hydrogen oxidation reaction site, because in this case, hydrogen molecule can be dissociatively adsorbed on the platinum group surface. It's easy. And once it is adsorbed, just give up the electron, and then it becomes proton and electron. Then electron goes to this way, protons go through PEM and come to the other side. The other side, we must reduce oxygen. Oxygen reduction can go to the hydrogen peroxide or water. Of course, we want to reduce oxygen to water. So in that case, we must break this OO double bond, so which is more difficult than to make hydrogen peroxide. In the case of hydrogen peroxide, you just get 2 protons to the both sides. But in this case, you must have a more complicated 4 electron, 4 proton steps. So we need very good catalyst. So we call it electrocatalyst. Now, oxygen reduction is carried out in our body every second. So we eat something, then it is oxidized by oxygen to generate CO2 and water and ATP and energy. So at the end, actually cytochrome C oxidase reduce the oxygen to water. In our body, we don't use platinum. We just use copper and iron, some magnesium, something. So O2 is reduced to water without precious metal inside our body. Maybe it is interesting to see how much oxygen we are reducing per day. How much liter? You can calculate it easily based on this calorie, and you know how much calorie we are consuming. But anyway, it is interesting to see. Actually, it's quite a lot. So as I showed, I mentioned the electrocatalyst in these figures, but on the other hand, however, when I was in Hokkaido University, I always wrote like this. So our concern was mainly in this side, because I was a professor in physical chemistry in science department. But once I came to NIMS, National Institute of Material Science, which is National Institute, we must work also more practical side. So we started electrocatalyst more seriously. So first example is the oxygen reduction catalyst. Such effective, precise metal-free electrocatalyst. So, of course, many people have been studying this, and one of the candidates were nitrogen-doped carbon for oxygen reduction reaction. many people carried out research on theoretically or experimentally. So in the case of nitrogen-doped carbon, the electron-accepting behavior of nitrogen species makes the net positive charge on neighboring carbon atoms where oxygen is absorbed. Of course, oxygen must be absorbed first as a first step. So nitrogen dope is good, but also if the boron dope carbon is also good, in the case of boron dope carbon, oxygen absorbed on boron atom itself. And some people mention boron and nitrogen co-doped carbon is much better. So we thought, what happens if all carbon atoms are replaced by boron and nitrogen? That is boron nitride. So can boron nitride be an electrocatalyst for oxygen reduction reaction? That is our first question or first motivation. So the boron nitride is known to have the same structure as graphite. Of course, graphite is conductive, but what about boron nitride? Boron nitride is here. So it's kind of a so-called 3,5 semiconductor group. So the indium antimony has a 0.17 electron volt, gallium arsenide, 1.42 electron volt energy gap, aluminum phosphide, it's a 2.43. Boron nitride has the energy gap of 6 electron volts, which means it is insulator. So the boron nitride has a similar structure with graphite, but is an insulator. Of course, if it is insulator, people easily think it is not good for electrocatalysts. So BN can be an electrocatalyst for oxygen reaction. So people say no. However, there's a possibility of electronic structure modulation by defects and support. So we did the first theoretical calculation for the possibilities. So then we calculated various types of boron nitride, introducing the defects first. So in the case of some defects, we found that the some intergap states are introduced, but more drastic effect was observed when the boron nitride is placed on the surface or on the support. This is a calculation of boron nitride on nickel 111. So this is the boron nitride itself. There's a huge energy gap, but once it is placed on nickel 111, actually there's lots of residual states within the gap. So there's a possibility that it can be more electronically conductive. And furthermore, we carried out free energy calculation for oxygen reduction. But the nickel is not good for experimental oxygen reduction reactions substrate because the nickel can be oxidized or became a hydroxide in alkaline solution or dissolve in acidic solution. So we used gold 111. Of course, gold is still precise metal, but maybe as a proof of concept study, it may be nice. So if we calculated gold for the this energy gap, compared with nickel, the density of state is relatively small, but still there's a possibility. And also we calculated the free energy for the 4-electron process to water or the 2-electron process to hydrogen oxide. So this is the reaction coordinate and free energy change starting from oxygen to water. In this case, actually, there's a uphill state, but in the case of the hydrogen peroxide formation, relatively smooth reaction is expected. So although it's not the final goal, but still there's a possibility. So we carried out experimentally. So we used gold 111 substrate. Then we carried out the rotating disk electrodes. Actually, this is the oxygen reduction. Theoretical oxygen reduction potential is far positive, but in the case of bare gold, this is very bad. So this is the electrode is rotated, so the oxygen supply is controlled. Then first we use boron nitride nanotube. It looks better. It's shifted to positive. Right. So then boron nitride nanotube has a not well contact with substrate, so we use boron nitride nanosheet. So these are the nanosheet, and you can see even the atomic fringe. So in the case of boron nitride nanosheet, which is much better than nanotube and far better than the, so it's more than 250 millivolts shift or something. So we demonstrated, of course, gold is very bad in our substrate, and the boron nitride is insulating material. So the combination of bars gives effective electrocatalyst for oxygen reduction reaction. So this is the summary. So glassy carbon case, even with boron nitride modification, nothing. In the case of gold with boron nitride, it's become like that. In the case of platinum, platinum is itself is quite good, and the modification or the surface modification boron nitride became a little worse actually. So the compared with platinum, it's very bad, but still there's a possibility of improvement. Or boron nitride is acting as electrocatalyst. Another thing is you must notice is that this limiting current is quite small compared with platinum, because in the case of platinum, oxygen is reduced to water, 4 electrons. In this case, oxygen is reduced to hydrogen peroxide, 2 electrons. It's bad, but still it works. So then we carried out various other calculations, using the small boron nitride and so on, so that we found theoretically interaction at the edge of boron nitride with gold is very important to reduce it. So we add gold nanoparticle on top of boron nitride so that the interaction will increase. So then this is the results. So this is the gold, boron nitride nanosheet gold modification. Then on top, we added gold nanoparticle. It became better. Not only the potential shifted positively, but also the limiting current increased, which means there's a subroute of the oxygen reduction to water is open. Another way to directly detect the fraction of hydrogen peroxide formation and oxygen reduction is the rotating ring disk electrode study. So usually for the oxygen reduction reaction, we rotate the electrodes so that the oxygen supply can be controlled. Then in this case, we have a ring electrode surrounding the disk electrode, keep the potential 0.9 volt, where at this potential, hydrogen peroxide can be oxidized. So it means that if oxygen is reduced to hydrogen peroxide here, then hydrogen peroxide oxidized at the ring. So in the case of gold, this one, and this is the disk electrode. Disk electrode means the reduction of oxygen. Then the ring current is showing the hydrogen peroxide oxidation. So in the case of gold, there are lots of hydrogen peroxide. On the other hand, other limitation is platinum. Platinum has a very large disk current because of the very high catalytic activities, and ring current is very small. Because in the case of platinum, oxygen reduced to water. Water is not oxidized at this potential, so there's no current here. So this ring current to this current ratio is very important. In the case of gold, BNNS gold modification case, it's this current increase, but ring current also increases. However, by using the gold nanocluster modification on top of the boron nitride nanosheet, actually this current increases, but ring current decreases. So we can calculate the fraction of the H2O formation as a function potential. This is a platinum, almost 100%. This is a gold. So then this is the boron nitride nanosheet modified gold, and this is the gold nanocluster modified boron nitride nanosheet gold cases. So it improved also the fraction of water formation, 60%. Okay. So then, of course, we need to know why. Then we again calculated the free energy diagram utilizing the small gold nanocluster on top of boron nitride. It showed that the this step, which inhibits whole electron reduction step, is stabilized quite well. So the small gold nanocluster stabilized here, so that this 4-electron process is started. Okay, so if it is the case, then it is better to have a small gold nanocluster. That's what we thought. Then we used the size controlled small gold nanocluster, in this case 5 nanometers cluster. So you can show it. Yeah, so before gold nanocluster was randomly distributed, but in this case we have controlled the size of gold nanocluster to the 5 nanometer. So then this is the result. So compared with even this one, it's very close to the platinum. This current increase, ring current decreases. So the fraction of water formation is almost 80%, very close to the platinum. Okay. So then accidentally we found that this electrode is also effective for hydrogen evolution. So this is the oxygen reduction current by rotating the electrode with different rotating rate. So usually we stop here, but at one time, my postdoc actually applied more negative potential. We see some current increase. What is this? Then maybe hydrogen evolution. So this is bare gold, bare platinum. So gold is very bad compared to platinum. Then by using platinum, gold modified with boron nitride nanosheet, actually overpotential decreased quite a lot. So the boron nitride nanosheet gold is very good, but not boron nitride nanosheet glassy carbon, no platinum. So then why this works? This is the one I showed. Then of course, thermodynamically, there shouldn't be any difference, but these are the electrocatalytic problem. So the hydrogen evolution reaction is simple, but still it's a two-step process. So first process is a proton received electron and becomes hydrogen atom or absorbs hydrogen on the metal. And then these hydrogen atoms combine together to form hydrogen, or the second electrochemical reactions proceed. So the energetically like this. So the first step, if it is in vacuum, it goes very high, but by absorbing on the metal, depending on the absorption energy of hydrogen, the intermediate state changes from here to here, depending on the absorption energy. Actually, if you plot the rate of hydrogen evolution reaction as a function of the metal hydrogen bond, it is like this. It's called famous volcano plots. So in this region, actually, by increasing the absorption energy means the decreasing this height, the higher this energy, the higher the rate, because it's going down. But if it goes down too much, then it becomes harder for the second step. So it goes like that. So this is a famous plot. Then we also calculated for the boron nitride case for this calculation. If it is the monolayer boron nitride, it's very high. So it's not good. However, by using several types of the small boron nitride nanoribbons of boronite island, and so on and so forth. Then there's a very wide variety of the adsorption states, and actually there's several sites which allow the very good intermediate state. So actually these are these edge atoms. So edge atoms plays very important roles. So we then thought if edge atoms is important, smaller BN should be more active. So then we carried out the modification by size selective boronitride. So this is the boronitride nanosheet with this size distribution. Then we use membrane filter to separate out these boronitride. So by using this one, then hydrogen evolution reaction is like this. As expected, the smaller the boronitride nanosheet, the higher the activity. Actually, the highest activity is very close to platinum, only 50 millivolt difference or something like that. So that is very good. Okay, so then, since then, we published a paper, theoretical paper in 2013, and the experimental paper in 2014. Actually, the boron nitride for hydrogen evolution reaction, oxygen reduction, the number of papers and number of citations increased quite dramatically. So people are very much interested in this system. Of course, not only boron nitride, there's another possibility as well. Okay, now I'll go to the battery. So this is, again, back to the energy flow renewable systems. Of course, batteries are another important devices, particularly for short-term storage, and also the electric vehicle. Of course, every day people are talking about the electric vehicle, so the number of electric vehicles is increasing quite dramatically, and this is the forecast of that. So US, of course, China, Japan is small, Europe, India, this is green Korea. And then also this is the amount, right? Lithium-ion battery supply chain prediction. So in both cases, the lithium-ion battery is expected to grow quite a lot. But not only for the electric vehicle, but also, of course, as shown before here, that the energy storage use is very important, because as the natural energy increases, you need to store it. In Japan, in Kyushu Island, the power company many times actually asked the solar cell, solar battery, or solar electricity generator to stop it or disconnect the electricity, because sometimes more electricity is generated than the consumptions. But if we can store it, it's much better. So the energy storage use is predicted to become more and more. So its number of expected energy storage use of the battery is high. This is Japan, Korea is reasonably high, Europe, US, China. Okay, but I must admit that even when I wrote this, there's no battery. We didn't think battery is become so important, or also the battery is very old devices, so not new or something. So we did, even the application, I didn't write it, but it becomes very important. I'm very much involved now. So, of course, Nobel Prize in Chemistry 2019 was awarded. Professor Goodenough, Professor Whittingham, and Dr. Yoshino of Asahi Kasai. So, actually, when I was doing PhD in Australia, actually, I have one article in this book. This is actually edited by Goodenough and Whittingham. Of course, at that time, my paper was on photoelectrochemical production of hydrogen with Bockris and me. in the symposium on the ACS in 1976. But anyway, so I knew his name and so on. So then I went to Oxford, where Professor Goodenough was moved from MIT to Oxford Inorganic Chemistry Laboratory just before I joined. So I was asked to come or joined. So this is 1978 Oxford Inorganic Chemistry Laboratory, very old building. The funny thing is that when I visited in 2017, building became much new. They polished, I think. And also another change was here. There's a plaque showing that the important finding in this building. One is the Professor Hodgkins Nobel Prize winner on the X-ray study. And the another one is glucose sensor by my boss, Professor Hill. And the last one is Professor Goodenough and colleague from the lithium-ion battery, the material research bulletin by Professor Goodenough. And first author is Dr. Mizushima. Actually, this is the list of the people in that inorganic chemistry laboratory at that time. So Professor Goodenough, Mizushima, Hill, and my name is there. So anyway, so this is the photo of Professor Goodenough in 2016, 3 years before the Nobel Prize in Hawaii. He was at that time over 90, but he was very active or very loudly laughing. And then in 2017, we awarded Nimbus Award to the Professor Yoshino and Professor Dr. Mizushima in 2017. And also I was the program officer of the ALCA Spring, which is the Japanese national project on next generation batteries. So that is 1.5 billion yen per year for 10 years. Actually, this is the last year of this project. In this project, we are working on the all solid-state batteries, sulfide base, oxide base, lithium sulfur, metal air, and magnesium, and so on. And also we have a battery research platform in NIMS, AIST, and Waseda University to support research. We have a very good facility for that battery systems. So this battery research platform carries or got about 20 million US dollar in 2012. With the that money, we have a super dry rooms, battery fabrication labs, and lots of advanced equipment, which allows the airtight transfer from grab box or the super dry room to these SEM, XPS, and so on and so forth. And recently we added new method, X-ray absorption spectroscopy, lab ZAFs, and also X-ray CT. Both are used for operant measurement. And even we have a near ambient pressure XPS. So these are very good systems. So we are working using this system in our laboratory or institute. So in our group, we are working on lithium-ion batteries. The lithium-ion battery is, this is the capacity and voltage plots, and then the lithium-ion batteries, as I mentioned before, the theoretically very high energy density because it uses only oxygen as active material, so also lithium metal anode. So the by the reaction of lithium becomes lithium plus, and the lithium plus reacted with oxygen, and reduction becomes Li2O2, which is kept in this porous carbon electrons. So this looks good. And so we started NIMS SoftBank Advanced Technology Development Center for the development of lightweight battery to be used on the high altitude platform station, HAPS so-called. So this is the station for the smartphones and so on. So not on the land, but on the high altitude air. So about 20 kilometers above. So the international flight is flying about something like 10 kilometers. So this is 20 kilometers above. But so this is about 70, 80, or 100 meter length with the solar panels flying over the Earth. But in night, of course, we need a battery. But so because of this, we need very light battery. So we started working on the lithium battery, but the problem is very low cycle numbers. So it degrades very quickly. And then we recently reviewed many papers published so far, and they plotted energy density as a function of cycles, or cycles as a function of energy density. So our results are one of the top, but still the number is very low. So we are required to have something like over 500 watt per kilogram. But in that case, we still have only something like 10, 15, something like that. So it's very bad. So what is the problem? There are lots of problems. Anode side, metal electrode, we have a dendrite formation degradation metals, large overpotential degradation for the cathode, and the electrolyte itself degrade. So far we have worked on the cathode and electrolyte degradation by using various techniques. One is the mass spectroscopy in situ real time. So in this case, the cell is quite similar to the real cell. We have a very small amount of electrolyte, lithium metals combined together within this cell. And then we analyze the decomposed gas by online mass spectroscopy. So during the charge, actually we generate oxygen because the reaction. During the charge, Li2O2 become oxygen and lithium plus. So the oxygen, if it is only oxygen generated, it's good, but we have water and the CO2. CO2 comes from the decomposition of the electrolyte or the carbon cathode. So it's bad. So this is one of the cause of the degradation. We also carried out the various technique, using the various technique to detect the impurities, electrochemical consequences of microbalance, which I showed before, so that how these product adsorbs on the surface, rotating ring disk. By doing this, how much oxidation or reduction efficiency can be determined, and in situ Raman spectroscopy to determine what is on the surface, not only the Li2O2, but also the other product. So, and also we found that the products very much depend on the potential and also the impurity in the solution. Often people say the water contents in the solution in the battery is 50 ppm or something. It's quite good, they say, but if you convert it to the molar, it's a kind of millimolar, which is very high in the electrochemical sense. So water contributes much to the decomposition, then LiOH and something like that. So it's also, there's a HF involved because we use fluorine-based electrolyte. So now recently we started working on the anode, which is lithium metal. So we use X-ray CT, and also after the assembly we do the SEM EDX or something. So after the cell assembly, discharge charge and sealed in the laminate pack, we carried out the X-ray CT, which we don't need to be assembled. Then we assembly the cell and go to the SEM EDX EBSD. So this is the X-ray CT image before the discharge. We cannot distinguish lithium metal and the separator, but once we even just one discharge charge cycle, you can see there's a porous layer on top of the lithium metal. And then after 10 cycles, the lithium became very porous and very bad. So these are another cause of the degradation. We also carried out SEM, EDS measurement so that this porous layer has this porous lithium or the small lithium metal is surrounded by electrolyte originated something, some impurity. So it also causes the recyclability very bad. So by this technique, we want to improve much, but at the moment we are still struggling. But these surface science technique or electrochemical technique, including X-ray and so on, will be very useful to attack the problem, both in the fuel cell or battery or any other electrochemical energy conversion. So these combinations, synthesis, preparation, properties, reactivity, theory, calculation, measurement, structure, etc., by combining electrochemical surface science will lead to the efficient electrochemical energy conversion processes. As Professor Kim mentioned, this is some JPC journals in which many papers related to electrochemical surface sciences published. So if you are interested, please look at this one. So just before concluding my talk, I just want to mention a little bit about our institute. Our institute is National Institute of Material Science, established in 2001. Actually, it was originated Institute of Metals and Institute of Inorganic Materials, which are both under the Science and Technology agencies. But Science and Technology Agency and Ministry of Education were merged in 2001 to become next. At the same time, these two institutes merged to the National Institute of Material Science. And then since then, we have a lot of projects related to battery research platform, SoftBank Center, materialized project for all solid-state battery. Now, recently, we started the materials open platform for all solid battery with 10 Japanese industry aiming to the all solid batteries and so on. So our institute is close to Tokyo, about 50, 60 kilometers north, and this is the area view our site, and Tsukuba University, and the synchrotron radiation source. So this is a research city. We have about population of 200,000, but most of them are very close to here, and out of 200,000, it is said 7,000 or 9,000 people got PhD. And then this is another view. We have a Mount Tsukuba here, my back, and also we have I'm here at the University of Tsukuba Photon Factory. In front of our institute is the JAXA, which is the Japanese Space Center, or like NASA. We have a training center for the space astronauts, etc. So from the top of our building, we can see the Mount Fuji to Mount Asama, very nice. In winter, we can see very nice view. It is about 150 kilometers away from our institute, but we can see both Mount Fuji and Mount Asama. So our institute is relatively high ranked based on the highly cited papers. So in total, number 6 in Japan, Tokyo, Kyoto, Riken, Osaka, Tohoku. But in chemistry, we are number 3, Kyoto, Tokyo, NIMS. Physics, number 4. And material science, we are the top. So we are relatively good institute. So if you are interested, you can join as the world top class leader to the PhD student. So we are hoping to collaborate with you. Thank you very much.
Well, thank you, Professor Wosaki, for your very interesting and extensive range of topics. We really appreciate for your participation today. Now the session is open for questions or comments. First from students. While they are making questions, I have a very brief, simple. Oh, there is one appeared in a chatting panel.
I got in that particular current tenses and other values. So Okay, so I will answer. Just a minute. Okay, that's a long question. Okay, my question is as follows. Consider we are talking about taking oxygen reduction reaction activity curve in a different scan rate. Obviously, as the scan rate increases, the B current also increases. So why my question, if I do chronoamperometry at particular potential, what would be the current density we can get? So of course, the current density in the case of oxygen diffusion is slow. It's a gas. So then by rotating the disk, the oxygen supply increases, so the limiting current increases. But of course, the earlier part, the kinetic part, where is it? Okay, so some here. Okay. So in this case, actually, in this region, actually, in very small current region, actually the current is not affected the supply of oxygen. So in ordinary stationary electrodes, in the case of platinum, when it is become good, actually it's limited by the oxygen supply. Then in the earlier part, the reduction is controlled by reaction. So you can actually calculate the expected theoretical current by diffusion or solubilities or concentration of oxygen and so on. So we can know the theoretical current density by knowing the rotation rate and the rotation rate and the concentration and so on, temperature. So yeah, so that my question is considered. So my question, if I do chronoamperometry, chronoamperometry is the potential spent. Of course, depend on how you do. If you do the stationary, of course, the current decay. But if when by using the rotating the electrode, the current doesn't decay. It's because the current is the reactant is supplied constantly. Is it okay for the answer? Anyway, so this is chat. So the Hasak was asking something.
Yes, I was wondering about boron-doped diamond electrode. And even though boron-doped diamond electrode has very little amount of boron, not like boron nitride. And I was wondering whether boron-doped diamond electrode can behave.
Yeah, so boron-doped diamond is a p-type, and it become conductive. So many people studied boron nitride diamond, right?
Yes.
Very heavily doped. But so in that case, actually, the catalytic activity is relatively low.
Yes.
So in this case, also, see, boron nitride itself is not good. Okay. So the theoretical calculation shows, of course, boron nitride itself is very wide gap insulator, but if it is put on the platinum, on the gold or nickel or something, then the modulation, or actually boron nitride bent or something, the interaction makes the new state within the energy gap.
Okay. Thank you. Any other questions? Not only from students, but also from professors this time. Oh, there is another one.
What would happen if you deposit other 2D nanosheet? Like, would it work even better? Or I don't know whether even better or something, but but I think, actually, the many people, as I mentioned, the paper, the increase of the paper after, this one, actually, the increase of this includes many attempts. many other materials. So depend on, also we actually did combination with this boron nitride with graphene, reduced graphene. Sometimes it's better. And graphene itself also works. So if I knew it works better, I did work and I might have published already or something. But so you can try. Or the point is, I think nowadays we can do. I lost my slide. Yeah, do the theoretical calculation relatively easily, so that it is better to see if it works or not. And also we do BNC, something like that. Yeah. And actually, but at the moment, now I'm finishing my work, activity, so you can do that.
Okay. Any other questions? And if not, Kohei, would you please terminate the screen sharing? And at the same time, please keep smiling for next 10-15 seconds so that our staff can take photo. And I invite everyone in the class, turn on your video camera so that our staff can take your very nice face photos.
Okay.
And keep smiling.
Smiling.
Keep smiling for 10 seconds. Okay. Okay, I can see them all, and our staff must have finished taking photos. And Kohei, I really appreciate for your participation. And before I close my seminar today, I'm going to introduce our next speaker. Here it is.
Still black.
And next,
Okay.
there is a young professor from Korea University, Professor Song Ho-yu. That's some mistake there. And Department of Chemical and Biological Engineering. The title is Operando Visualization of Electrochemical Reactions in Next Generation Batteries. And by the way, next seminar is the final one for this semester. And everybody should remember that seminar report is due by noon of June 23rd. So noon on June 23rd. I hope you don't miss the deadline. And I'll see you next Thursday for final seminar. And Kohei, thank you very much for your wonderful presentation. Thank you very much.
Thank you. So bye-bye. Bye-bye.
Bye.